Thank you. Hello, everyone. I'm Jayant, and I'll explain the survey paper Foundation Models for Time Series, a survey. So, we'll explore how the ideas that reshaped language and vision AI, large pre trained transformers, are now transforming sequential data analysis. So, the next is why foundation models for time series. So let's begin with the motivation. In NLP and computer vision, models like BERT, GPT, and VIT are pre-trained once on massive corpora and then adapted to countless downstream tasks. So this foundation model paradigm, it has dramatically cut development time. It cut the development time and improved performance. So, time series analysis, that is forecasting energy demand, detecting anomalies in sensor streams, predicting financial trends. It has traditionally required custom models for each dataset or each task. That means bespoke future engineering, hyperparameter tuning, and retraining whenever the problem changes. So here are two key challenges stand in the way of bringing foundation models to time series. The first one is long range dependencies. Vital signals can depend on patterns, weeks, months, or even years old. Uh, Classic RNNs, recurrent neural networks, struggle here. So heterogeneity and non-stationarity, like time series come in all shapes, multivariate sensor arrays, financial tick data, irregularly sampled logs, and their statistical properties can shift over time. So, what the survey asks is, can we pre-train one large model on many kinds of series and then use it out of the box or with minimal fine tuning for new time series tasks? So, the next slide, yeah. Defining a time series foundation model. So, what exactly counts as a foundation model in this context? So, it's basically a large neural network, typically transformer based. So, that is pre trained on a broad, diverse corpus of time series. During pre training, it learns generic temporal patterns, seasonality, trends, anomalies, across domains. After pre-training, we can apply it in several ways. For example, zero shot forecasting on a new series with no additional training, and also few shot fine tuning on a small amount of target data to specialize. Representation extraction, like for tasks like classification or anomaly detection using the model's internal embeddings. So this basically mirrors NLP. So we might use GPT-3 as is to generate text or fine tune it on our own data set. Uh, Fine tune it on your own data set or extract sentence embeddings for downstream tasks. And next is taxonomy overview. So the paper's core contribution is a taxonomy to categorize the growing field of time series foundation models. So It covers six dimensions. The first dimension is architecture type. So it can be encoder, decoder, encoder only, or LLM adaptation. Input strategy, that is like raw time step tokens versus patch embeddings. Output mode, deterministic point forecast versus full probabilistic distributions. And the next is scope, univariate one series or like versus multivariate many signals. Scale, it can be a lightweight, a few millions of parameters, to massive like billions of parameters. And the training objective, supervised forecasting, masked modeling, next token prediction, contrastive learning. So this structure helps us compare any new model quickly by checking where it falls on these axes. So the next slide, key architecture families. So the first architecture is encoder decoder. It is inherited from original transformers, that is patch TST. So encoder processes the history and the decoder generates the future sequence. And next architecture is decoder only. So it is normally GPT style auto-regressive generation of future points, like for example, times FM. It is naturally suited for step-by-step forecasting. And the next architecture is encoder only. So it is a BERT style masked reconstruction, learning latent representations. For example, time BERT or moment models. Uh, they are good for fine tuning on varied tasks. And next is LLM adaptation. It is where numeric sequences are quantized into tokens and fed into a frozen language model. Like for example, Chronos reuses T5 or GPT-3 prompts for forecasting. So this leverages existing huge LLMs but requires careful token design. So this is LLM adaptation. So each style has its own pros and cons, like in terms of complexity, transferability, and inference cost. And the next is input tokenization, raw versus patch. So next, how to present the series. I mean, in two ways, either raw or patch. In raw type, each time step is one token. Each time step is one token. It is straightforward but can be very long. For example, thousands of tokens, leading to high attention costs. Patch. In patch, we group consecutive steps into fixed length chunks, like 16 or 64 points, and embed each chunk as a single token. So this drastically reduces sequence length and forces the model to learn local patterns within patches. Patch TST popularized this in 2022, uh, showing major speedups and accuracy gains on long horizon tasks. So choosing patch size is a hyperparameter. Too small and you lose efficiency, and if too large, then you may lose fine grained detail. So next, it's output modes. Foundation models differ in what they predict, either deterministic or probabilistic. Coming to deterministic, uh, point forecast only, optimized via MAC or Huber loss. Many early transformer-based TS models did this. It is fast but blind to uncertainty. And the next is probabilistic, full forecasting distributions trained via cross entropy on quantized tokens, chronos, or via likelihood on parametric mixtures like Toto with its student T mixture head. Output is a mean and confidence bands, essential for risk sensitive domains like finance or supply chain. So the survey notes a trend like the first gen models were mostly deterministic. More recent work emphasizes probabilistic focus. And next slide is like univariate versus multivariate modeling. The another axis is scope. So coming to univariate, one series at a time. It is simpler, good for isolated tasks. For example, single stock forecasting, single sensor stream, etc. Uh, And next, coming to multivariate, jointly model multiple correlated series. For example, several IoT sensors on the same machine. Capturing cross-signal dependencies can improve accuracy, but it also adds complexity. Architectures like Tutu alternate space-wise blocks like mixing across variables with time-wise blocks like mixing across steps to handle this efficiently. The most early foundation models were univariate, but the newer ones increasingly support multivariate input natively. In the next, going to next slide, model scale spectrum. Foundation models span like huge scales. They can be tiny, like 1 to maybe 10 million parameters. For example, tiny time mixtures TTM, lightweight MLP mixer style, few short performance gains, and it is edge deployable. The mid ones, 100 to 500 million parameters, for example, patch DST, Chronos, Moirai, uh, core transformer sizes, and balanced performance and cost. And the massive ones, more than 1 billion parameters. For example, time MOE, which is 2.4 billion parameter, Toto, hundreds of millions trained on 1 trillion, 1 T data points. That is 1 trillion data points. High capacity, best zero shot generalization, but need big compute. So, the survey it emphasizes that uh, smaller models, like with good design, can still deliver strong results, but scaling up often yields new capabilities. And coming to the next slide, the surveyed models, foundation models, the highlights. So here are 10 representative models from the paper. Times FM by Google. It is a decoder only on 100 billion points. Strong zero shot. Patch DST. Patch based encoder decoder. Long horizon SOTA. Chronos. AWS. Quantization plus T5. Next token probabilistic forecasting. Time GPT by Nixtla. Univariate forecasting API on 100 billion data. Tiny time mixtures. Tiny time mixers by IBM. A 1 million parameter MLP mixer. Few short gains. Timer Excel. Singua, Generative Multivariate Decoder, Time MOE, sparse mixture of experts at 2.4 billion parameters, uh, Moment, CMU, masked pre-training on time series pile, open models, Moirai by Salesforce, a universal forecaster, multi-frequency support, Toto by Datadog, space-time factorized transformer plus student T mixture, which is trained on 1 trillion points, 1 trillion points, 1T points. Okay. So the survey actually reviews 20 to 30 models, but these showcase like common design choices and scale levels. And the next slide is training data and benchmarks. So how are these models evaluated? First, pre-training corpora, the datasets, public archives, for example, LOTSA, LOTSA, UCR, M4, plus proprietary streams like Datadogs, 1T points, synthetic Gaussian data for Chronos, and also zero shot. Many foundation models outperform classical baselines and even specialized deep nets without any fine tuning, which is a key hallmark of generalization. Next is few shot. With just 5 to 10% of target data, pre-trained models often exceed from scratch training thanks to a strong initialization and task diversity. Besides forecasting MSC or MAP, models are tested on classification like UCR archive, anomaly detection, NAB, and imputation tasks, though forecasting remains the primary benchmark. So, like the survey, it calls for standardized benchmark suits to fairly compare new models across multiple tasks. Coming to the next slide, uh, limitations that are highlighted. Despite these advances, the survey flags key challenges. And the first one is data silos and bias. So that means pre-training corpora are fragmented. Models could risk underperforming on underrepresented domains. Non-stationarity, like for example, that means distribution shifts over time. For example, pre versus post COVID can degrade zero shot performance. Compute costs. Large models require expensive infrastructure for training and inference. Interpretability. Transformers remain black boxes, like attention weights alone don't guarantee transparency. And task adaptation. A focused model may need some fine tuning to excel at classification or anomaly detection. Like addressing these challenges will be crucial for a real world adoption, like for especially in regulated or resource constrained settings. And the next is future directions. So the authors outline several promising avenues. Like the first one is larger, more varied corpora, like including synthetic data, so that we can cover rare patterns. Multi-model integration, like blending time series with text, graphs or images for richer context. So efficient scaling, hierarchical, sparse attention, and mixture of experts to handle long sequences and many variables. Domain specific models, like for, embedding prior knowledge for healthcare, finance, IoT, etc. Parameter efficient adaptation, adapters, prefix tuning for quick personalization with minimal compute. And the next is robust uncertainty and explainability. So better probabilistic methods and tools to trust model outputs. So these directions, they mirror the trajectory of NLP. Bigger, broader data, more efficient architectures, and stronger emphasis on trust and interpretability. So and the next slide. So the final slide is about takeaways and closing. So to summarize, uh, transformers and foundation model principles are arriving in time series, like promising one model to rule them all. So a six-axis taxonomy, it helps us navigate hundreds of emerging models. Real-world results show impressive zero and few shot performance on forecasting and beyond. Significant challenges remain in data diversity. So remain in data diversity, scaling, and interpretability. The field is rapidly evolving, means like expect new pre-training corpora, efficient large models, and multi-model variants in the coming year. So this is what the paper like explains about. This is what is in the paper. So this is my explanation of the survey paper.